Welcome back, everyone. Our topic for this video is the energy associated with light. Our agenda, this actually is covering the next couple videos. This video is all about right here, the energy of light. There's an equation we're going to learn, and you're going to do some practice utilizing this equation. And very briefly, we're going to see another of those images showing the spectrum of light. Because once we know the equation and what the energy of light is based on, we can do some quick, pretty easy comparisons by what types of light have the most energy, what types of light have the least energy. Okay, for my comic right here, maybe this is aging me a little bit, but if you remember, I think you would have been in like middle school, maybe elementary school, but it was a while ago. There was this picture that kind of caught the internet by storm. There was this dress, and here's just a little sliver of it. And people got into debates because some people saw this image as being white and gold, and some people saw the image of being blue, I think, and black. And what color do you see? What color for this little snapshot, this little sliver of the dress do you see? What two colors? I always see white and gold, but different people saw different things. And the explanation, the best explanation for this is it has to do with how your brain is interpreting not just these colors, but also how much light, how much brightness there is in your surrounding peripheral vision. For example, if you have a lot of light shining in your peripheral, people tended to see this more as like a black and blue or a brown and blue. Or if it was a darker surroundings, people saw this more as a white and gold. I always see it as white and gold, but this was a funny example of, again, color is all up here. There is no natural red. The universe doesn't have really red light. It just has a certain wavelength wave. And your brain interprets that particular size wavelength wave as being the color red. That's why, as one of my optional videos alluded to and went into more detail, color is frankly an illusion. And you don't know if what you're seeing as red is the same thing as what other people are seeing. Anyway, that's why I have that comic right here, right there. This is our big unit, remember? And hopefully by now you recognize that, well, all right, we know some physics about both how we hear sound and how we see. And last week was all about how we are able to see images on our phone. So in this big question, how do you take, send, and view a snap, we've more or less covered this part. Okay, we've understood how you view an Instagram post on your phone. Okay, on that screen, those three colors, RGB, mixing those colors together. We also understand how we hear it. So if someone posted a quick video, whether it's on Snapchat or I don't know, their Instagram story post, we have a decent idea of this. We're still working on these two, taking an image. So maybe we'll spend a little time at the technology of like cameras and microphones, but that's actually not too bad. That's based on a lot of physics we've already done. And also our big topic that we're actually getting into next is how do we send information on our phones? Well, we're not explicitly answering this week. The physics we're going over right now, at least a good chunk of it, is going to help us understand this piece. So that's what we're working on right now. So let's get into the energy of light. Remember, Einstein really brought to our attention that light simply isn't a wave. Even though there was some back and forth. Newton thought it was a particle. Then there was a lot of experimentation showing that it was a wave. Einstein found out, well, no, it's not really a wave. It's kind of both. And in fact, again, everything is kind of both. Okay, that's important because the energy of classical waves, sound waves, waves on a string, ocean waves, that's based on the amplitude of the wave. I have a more energetic sound wave if I'm speaking louder. Because you remember, sound waves, the amplitude is what determines the loudness. I have lower energy waves if I'm speaking quietly, because if I'm speaking quietly, that's low amplitude. Same thing, think of like an ocean wave. A wave with a little tiny amplitude probably doesn't have a whole lot of energy, but a tsunami, oh my gosh, a huge amplitude wave, that has way more energy. For light, and this is what partially the photoelectric effect showed, it's not coming from the amplitude. If I have a really big amplitude light wave, or if I have a really intense, a huge number of light waves striking this metal plate, that didn't really determine whether or not electrons were kicked loose. It had to do with the frequency. So Einstein helped show that it has to do with the frequency, and then there's another physicist around Einstein's time, Maxwell Planck, who came up with an equation, and that's what we're going to go over right now. The energy of light is based on two things. It's actually a pretty easy looking equation. It's based on h, and that's being multiplied by f, where E is the energy, and remember we're measuring energy in this class in joules, and F is the frequency. We measure frequency in hertz. Okay, pretty basic equation. But we don't know what this H is, so we gotta figure out what H is. So right now the equation's looking fantastic. There's no square roots. There's not even anything like the denominator, right, in this of this version of the equation. But we need to know H. It's a constant. Very similar to how for that force of gravity equation, F equals gmm divided by r squared, that g, 6.67 times 10 to the negative 11th, that's a constant. H is a constant as well, and it's known as Planck's constant. And Planck's constant is a really tiny number. Look at this exponent. It's 6.6 times 10 to the negative 34. Again, if you're taking notes, you probably want to write this down because we're going to do some math practice where you're going to need to know this number. You're always plugging this in for H. So this equation really just has two unknowns. So if I give you the frequency of, say, blue light, it's pretty easy to calculate the energy of blue light. Now, these energies are actually going to be really tiny because one single light wave is, well, remember, the scale is puny. It's going to have a really small amount of energy. But of course, things like flashlights and light bulbs and fires and the sun, obviously, they're emitting prodigious, huge amounts of light waves, and therefore the energy adds up. But when you're calculating the energy of one individual wave, you're going to be getting really small numbers. One quick aside, there is another way that physicists classically measure the energy of light, and that's using a unit known as the electron volt. Do you remember voltage? Well, an electron volt, that's like how much energy is associated with giving one single electron 1 volt, like a 1 volt battery across one electron. This number, these units kind of scale more with the small size of light waves. We're not going to do any calculations using this unit. I bring it up because we might see graphs or diagrams that are labeling energy as electron volts. It's still energy. Just like if I showed you a graph that was measuring distance in, I don't know, kilometers or inches, it's still distance, right? Even though we usually use meters, it's just another way to measure distance. Electron volt is another way to measure energy. Also, don't forget, because you might need it for the assignment associated with the energy of light, the speed of light is constant, and here's our equation for the speed of light waves. V equals f lambda, or for light, C equals f lambda. These two things are being multiplied. Okay? So that's the equation. Let's now just remind ourselves the spectrum of light. Remember, visible light is just one tiny sliver. There's all these other types, from radio waves to ultraviolet to infrared to gamma waves. And they're really just different based on their size. Radio waves are the largest size waves. They can scale on the order of mountains. Gamma waves are the smallest size waves, the size of like atomic nuclei. On this diagram, I have the biggest waves over here, the smallest waves, smallest wavelengths over here. Which side do I have the largest frequency, on the left side or on the right side? Where is frequency the biggest? It's on the right side, of course. And again, remember from this equation, since C is a constant, these two things are kind of like opposites. If you have a big frequency, you must have a small wavelength because they have to equal the same thing. Gamma waves have really big frequencies and they have very small wavelengths. Okay, they match. So we learned in our last couple slides that the energy is based on the frequency, but we could pretty easily deduce that therefore the energy is also based on the wavelength. Small wavelength, big energy, or likewise, big frequency, big energy. So what color light has the smallest amount of energy? What color of light? It's red light, okay? Because red light has the biggest wavelength, or, just as valid, it has the smallest frequency. So radio waves have the lowest amount of energy, gamma waves have the biggest amount of energy. Okay, so if I gave you a couple pictures of different size waves, you should probably be able to tell me which one has more or less energy. And of course, you might need to bust out that calculator or pull up a calculator app on your phone or use Google Calculator because you have a practice where you're doing some calculations based on this video. Okay, thanks for watching.